I have to admit, it's going to be about software systems engineering. So, cool. I also have to admit, I'm a mechanical engineer. Maybe that compensates a bit for lack of the other disciplines. And I also have to admit that I'm actually here to plug Dezyne. We've a few years back made it freely available to everyone. This is our model-based software systems engineering solution. And the title of this presentation is Compositional Correctness by Dezyne. So I'm not going to dive into too many details, but I want to make the case for building complicated systems that requires, well, first of all, models, which are founded in formal semantics. So I was inspired by Simon Sinek. Simon says, always start with the why you do things. So building complicated systems is utterly hard. We need all the help we can get. And the software engineering discipline has not been very mathematically inspired. There's a lot of computer science going on, but actually applying it in practice is utterly difficult. So that's where we want to make a step. It's a bold claim to make software engineering more like an engineering discipline. I'm not saying that it isn't, but engineering means applying maths to problems. And the way that we want to do that is, well, take formal methods mainstream. So we don't want to expose engineers to all the complexities of formal methods because they're even harder. If you want to, because in reality is difficult. Being exposed to the intricate complexities of reality is very difficult. So you don't want to be crushed under the complexities of the maths that you're trying to apply. So that's why we're trying to hide it. And we're doing that by making a language called Dezyne. So it is actually about, this was spelled the wrong way, of course, but it is about designing software in such a way that you can derive the actual implementation from that. And that implementation also incorporates the properties that you've designed into the design. I just want to briefly paint the spectrum of software that's out there. So things you can think of in the not simple but simpler side. It's basically transforming an input to an output. Algorithms that finish or functions that finish. They produce a clear-cut result. The output statements are just sequential, and they're definitely deterministic. And if you combine them, basically they behave like the sum of their parts. So this is the simple side of things. When you start making things more complicated, which often happens in practice, you get the systems thinking going on, and these are the things that you typically experience when you move towards those complexities. So you're still transforming input to output, but you have to take into account the entire history of all of your inputs. And that typically aggregates a state somewhere inside your system. And it drives what types of responses will come out next. They may not be the same as before because your state is now different. Your input history has changed. Typically systems, well, they might finish in a very long time, or they're continuous. Well, this is a fairly simple system, but this continuously monitors my health. I'm a diabetic. This is not typically the system I'm talking about. I'll have a slide later on with the actual systems. But we're talking about reactive systems instead of just a main function or concurrent systems. Systems that behave, software that behaves non-deterministically, so it becomes less predictable what you can expect. And you might even have emergent behavior because you can simply not know all the details anymore. So this is across the spectrum. I'm talking about this side today and not so much the other side, although I'm not trying to ignore that. So we have a challenge. It's a collective challenge. We have to balance two very complicated things, which is being productive and maintaining correctness, even assuming we could achieve that in the first place, while we're scaling up our ambition. So here's a picture I actually stole it from Joseph Safakis. So I need to give him credits. It's my version of the picture, but so I didn't literally see his picture, but it's inspired by what he made. It's showing different types of systems, like the one Michiel was talking about, the train system. With our method, we're not quite there yet, that we can actually build those types of systems. But we believe that in order to achieve that in society in a reasonable way, we need to change a few things. And one of them is that we need to start managing complexity through rigorous design. So what does that mean? Well, we need to start by formalizing our requirements. I don't mean that we need to think about our requirements carefully and that we need to write it down and that we have a certification body that approves it. No, mathematically formalizing requirements so that we actually know what it means instead of having them just in natural language where we think we know what it means. And I think we need to join a top-down approach. People think that's a waterfall, big design up front, anti-agile, but that's not what I mean. Whatever you can, what you know from the start, you need to refine stepwise down while verifying that you do a valid refinement of what you have specified, and marry that with a bottom-up approach where you've got you compose bits and pieces of which you have proven before that they're in as units are correct and that the composition also works as expected. So that's why we're making a language in order to help us to do that. I'm showing you VS Code here. Our language support is plugged into VS Code. And the language is basically comprises two properties. It allows you to describe your system structurally. And currently, we only support static structures, like the picture you see here. It's actually it's online, but I don't have the video. If you're interested, I can show you the video because it's on my laptop. It's a big Lego model of 4 bricks, Lego bricks that juggle balls. They're not actually juggling, but it's sorting different color balls. So there's a lot of hardware going on, and this software tries to supervise all that moving hardware to make it do what it does. So we've completely built this in Dezyne. So the language allows you to define the structure and the network of dependencies, but it also allows you to describe the behavior at every level. So you can see that our components are connected through ports, and ports are actually instances of interfaces, and our interfaces are behavioral, just like our components are. And this corresponds to what Michiel was talking before about systems interacting with an environment where different actors in that environment are not directly coupled. You have a multi-person conversation at the same time. That's what we are talking about when we say behavior. So you could describe this single component here. That's the source you're seeing. It has 4, 5, 6 ports, of which 2 are the same. And the behavior of the ports of the message exchange between the component and the environment is depicted here as state diagrams. So this describes the behavior across those ports. Now, from this, we need to connect these together to make that component fit inside that hole that's described by those port behaviors. And let's depict it like this. So just combining all of these state diagrams, which are concurrently running, quickly leads to, let's say, state space explosion. It's not actually an explosion. You can, if I render this in a readable way, you can still inspect this, and it's actually not too bad. But this is just this single component, and there are multiple components here. Currently, we're not able to render the picture of the entire system, but thank God we can actually describe the entire system, and we can actually verify that. Sorry, wrong way. This behavior is compliant with all of those sub-behaviors of their interfaces. 5 minutes left. Oh, I'll speed up. Sorry. So model checking our behavior is presented, if we find a counterexample, it's presented as a sequence diagram, which helps you find where you went in the wrong direction. And our language effectively supports interface design by contract, where our interfaces fully encapsulate the components and allow you to verify the components individually and then compositionally construct systems correctly. It's actually being used in industry. We are an Eindhoven-based company in the Netherlands. There's a bunch of high-tech multinationals there, and thank God they're our customers, paying for the development of all of this. And currently, we're active in semiconductor, healthcare, and automotive, just to name a few. Thermo Fisher was named by Michiel. I can name Philips and ASML and K&S as our customers. I'm going to skip over this. The most important message I have, it is freely available. You can find it yourselves. You can download this, inspect it, do research with it, or apply it in industry. And if you want commercial support, our company is very, send us an email. We're far from done. There's way more to do. Maybe I should open the floor up for some questions.